Imagine a 15-story steel building dropping out of the sky at supersonic speeds. Now imagine trying to land it gently on a small target, using nothing but a pillar of fire to slow its fall. For over 50 years, the standard operating procedure for spaceflight was incredibly wasteful. Engineers built multi-million-dollar, multi-stage machines, launched them into orbit, and then simply let the massive first stage burn up in the atmosphere or crash into the ocean. It is the economic equivalent of boarding a Boeing 747 in New York, flying it to London, and then throwing the entire airplane in the garbage upon arrival. Every single launch required a brand new rocket. The first major attempt to fix this extreme financial waste was the Space Shuttle. This was a vertical takeoff horizontal landing vehicle, or VTHL, designed to glide back to Earth and land on a runway like an airplane. But flying an airplane back from space comes with a heavy cost. The shuttle required massive wings, complex heat shielding, and heavy traditional landing gear. All that extra structure added so much weight and maintenance time that it failed to deliver on the promise of cheap, rapid reusability. To actually drive down the price of reaching orbit, engineers realized they needed to abandon the idea of wings entirely. They began looking at a method that replaced aerodynamic lift with pure, controlled thrust. Curiously, the solution they pursued was already mapped out by early pop culture. If you look at vintage illustrations from the 1950s, space vehicles almost always landed upright, resting vertically on their tail fins. The problem is that physics does not care about science fiction aesthetics. Pulling off a vertical takeoff, vertical landing, or VTVL, on Earth means taking a 500,000-kilogram cylinder, dropping it from an altitude of 70 kilometers, and managing a descent speed of 8,000 kilometers per hour. Nailing that exact sequence, controlling a falling skyscraper all the way to the ground, became the primary technical hurdle that stood between spaceflight as a rare event and spaceflight as a routine industry. Humanity's first successful vertical landing actually happened in the 1960s, just not on Earth. The Apollo lunar module used propulsive descent to touch down safely. But the Moon has no atmosphere and only 1/6 of Earth's gravity. A spacecraft can descend without fighting severe aerodynamic drag or intense friction heating. The first vehicle to prove vertical landing could work in Earth's gravity was an unsung prototype called the Macdonald Doug DCX. In 1993, this uncrrewed, cone-shaped rocket managed to hover and land successfully after a 100-meter test hop. Despite proving the concept, the DCX project lost its military funding in 1996. The prototype was eventually dismantled, and vertical landing technology stalled out for nearly 2 decades. The DCX showed that VTVL was theoretically possible, but scaling that technology from a low-altitude hop up to surviving the extreme violence of a returning orbital booster would require a complete hardware revolution. This trajectory arc plots a modern booster's path back to Earth, revealing 4 distinct phases of engineering. The first phase happens in the vacuum of space, where the rocket has to physically turn itself around using bursts of nitrogen cold gas from small thrusters. As the cylinder falls back into the thick lower atmosphere, it moves to phase 2. It relies on deployable aerodynamic grid fins to steer its descent, using the air pressure itself to guide the vehicle toward the landing zone. The third phase requires the main liquid propellant engines to reignite at supersonic speeds. Unlike early rockets, these specific engines must be capable of deep throttling, violently decelerating the vehicle without tearing the fuselage apart. Finally, for touchdown, the engine's gimbal, physically pivoting to provide thrust vector control, while the rocket deploys its landing legs to hit a pinpoint 50-meter target on the ground. There is zero margin for error. If the cold gas thrusters misfire, the grid fins jam, the engine fails to reignite, or the legs don't lock, the entire vehicle is destroyed on impact. After years of private development, the commercial space industry reached a major milestone in late 2015. In November, Blue Origin's new Shepard rocket executed a flawless vertical landing following a suborbital test flight. Just 1 month later, in December 2015, SpaceX's Falcon 9 accomplished an even more difficult feat, sticking the vertical landing of a massive orbital-class booster. In a span of 30 days, those 2 successful touchdowns proved that routine, propulsive rocket recovery was a functional reality. But the VTVL model comes with a strict engineering compromise. To land vertically, the rocket has to carry the dead weight of its landing legs, plus reserve a large portion of its heavy liquid propellant for those final deceleration burns. When comparing a throwaway rocket to a reusable one, carrying extra hardware and reserve fuel significantly reduces the payload mass it can push into orbit. But looking at cost per launch, recovering the first stage saves the most expensive components, the primary engines and avionics. Accepting a smaller payload capacity on each flight is mathematically worth it, because it completely avoids the massive expense of building a brand new $50 million booster from scratch every single time. Today, the industry has moved entirely past the experimental phase. Catching descending orbital boosters on autonomous ocean drone ships has become standard, expected protocol. The technology is now scaling up to massive, fully reusable systems like SpaceX's Starship and international projects like Callisto, pushing payload capacities back up while keeping operating costs down. By solving the falling skyscraper problem, engineers transitioned from the era of disposable vehicles to a model of routine reuse, making the science fiction dream of the 1950s a core part of the modern space economy.